Year 13, Year 1, Further Pure, Chapter 4, Matrices and their Inverses, Lesson 3, Matrices and Simultaneous Equations. So I want you to consider the pair of simultaneous equations 2x plus 3y equals 11, x minus y is equal to 3. Now, you know multiple ways of solving simultaneous equations. You know how to eliminate a variable, you know how to rearrange and substitute one equation into another. You also know how to solve a pair of simultaneous equations graphically. That's 3 methods there that you have worked with, both algebraic and graphical. However, we can also use matrix methods to solve linear simultaneous equations. So where does the matrix come into this? Well, can you see if I took the coefficients, and we'll write some in here, of the variables x and y, so 2, 1 vertically here, and then 3, negative 1 here. And I then create a matrix or vector as xy. Can you see that we can write the pair of simultaneous equations as a matrix equation? Now you can always check by multiplying back here 2x plus 3y and x minus y. So effectively, we get exactly back to where we were. So how can I now use a matrix method? Well, I have a matrix M multiplied by another matrix or vector xy, which equals 11, 3. Now, if I pre-multiply by m minus 1, I have m minus 1m multiplied by xy equals, and on the right-hand side, m minus 1, 11, 3. Now, what do we know about m minus 1m? It's equal to I. So effectively I have the identity multiplied by xy equals m minus 1 multiplied by 11, 3. But of course, the identity matrix applied to xy is just xy. So this then gives me xy equals m minus 1 applied to 11, 3. So if I can find the inverse matrix, I'm effectively applying it to both sides, and I can then work out what xy is. So xy equals m minus 1 applied to 11, 3. So our job is to find m minus 1 first of all, and we can do that using the information we know. So first thing, let's work out the determinant of our matrix M. And actually, I think we should probably identify what our matrix M actually is, and it's this matrix over here, the matrix of the coefficients of the x and y terms in the simultaneous equations. So the determinant of M is equal to negative 2 minus 3, it's negative 5. Now this method will only work if the determinant exists, i.e. if the matrix is non-singular, and that's important. So my inverse matrix is negative 1 over 5, and then let's remind ourselves that we need to swap over these components here, so that's negative 1 and that's 2, and then these components here we need to change their sign, so negative 3, negative 1. So there's my inverse matrix. So this then tells me that xy is equal to negative 1/5, negative 1, negative 3, negative 1, 2, pre-multiplying 11, 3. So let's do the multiplication, see what happens. So what do I start with? I start with negative 1 and negative 3 and 11, 3. So that's negative 1 times 11, negative 11, plus negative 3 multiplied by 3, which is 9, which gives me negative 20 here. And then, of course, I want to do this pair here, multiplying by this pair here. So that's negative 11 plus 6, which gives me negative 5. So when I then take 1/5 of both these items, negative 1/5 of both these items, I get 4 and 1. So xy is equal to 4, 1, which gives me x equals 4, y is equal to 1. And you can substitute those back into the original pair of simultaneous equations to check. 4 times 2 is 8, plus 3 times 1 is 11. 4 take away 1 is 3. It works. So in general, if we have a pair of simultaneous equations in the form ax plus by equals p, cx plus dy equals q, we can rewrite this as a matrix equation. Now, what would the matrix equation look like? Well, the matrix would be composed of these coefficients, so A, B, C, D. This is being applied to x, y, and giving us the answer PQ here. Or for simplicity, MXY equals PQ, where M is the green matrix A, B, C, D reading across the rows. Now, if M is non-singular, which means that the determinant of M cannot be equal to 0, and M inverse, the inverse matrix, exists, then we can solve the equation by saying that xy is equal to m minus 1 pq. But again, this only works if m is non-singular, so that the matrix inverse exists. So we're going to have a think about the geometrical interpretation of this. What does it mean when we have a pair of linear simultaneous equations? Well, the representation of these is, of course, two straight lines. So two equations in two unknowns are represented by two straight lines. Now, what happens when you have a pair of straight lines? Well, there are a few different possibilities. One possibility, of course, is that you have a pair of straight lines which intersect at a unique point. Another possibility is that you have a pair of straight lines which are parallel to each other. Now, a third possibility is that you have a straight line, and then by the definition of the lines, the other line is actually just the same line. So you have three possible different case scenarios. And what we're going to do in a minute is explore each of these cases in more detail. How do they relate to the linear simultaneous equations and the solutions of these linear simultaneous equations? And how do they relate back to the work we've just done on matrices and matrix inverses? So all this time, remember, we're working with two linear equations in two dimensions. Later on, in the second year of Further Pure, you'll be exploring what happens in 3 dimensions, and there are many, many more different cases that will occur. For the moment, we are looking at two straight lines in 2 dimensions, and these are the 3 cases that we must explore. So I want to have a look at this pair of simultaneous equations. So equation 1 is the equation 2x plus 3y is equal to 7, and it's represented on the graph by this red line here, 2x plus 3y equals 7, there we go. And then the second equation, which is 5x minus y equals 9, and that's represented by this gold coloured straight line over here. So the first case scenario, we're dealing with a unique solution, which is represented by the intersection of 2 straight lines. So let's look at the matrix equation, the equation that has the form mxy equals pq, and the pq in this case is 7, 9. Well, what's the matrix M? Well, remember, we look at the coefficients of the x and y terms. So we've got 2, 3, 5, negative 1 reading along horizontally across the rows. Now, remember what we said. We can solve this matrix equation if the matrix M has an inverse, i.e. if M has a determinant that is not equal to 0. So up over here, I'm going to work out the determinant of M, which is equal to 2 multiplied by negative 1, subtract 3 multiplied by 5, which comes to negative 17. So that's not equal to 0. Now this tells me straight away that M is non-singular, because its determinant is not equal to 0, which pleasingly tells me that the inverse of m minus 1, exists. Now, because it exists, we can solve this pair of simultaneous equations using the inverse matrix, applying it to both sides, or pre-multiplying to both sides, gives me xy equals m minus 1 applied to 7, 9. Now, the only thing I have to do is then work out what m minus 1 is actually equal to. So I know the determinant, it's negative 17, so I have minus 1 over 17 here. Now I need to remember what to do with the components, so swap these over, negative 1 and 2 swapped over like that, and then these two components must change signs, so negative 3 and negative 5. Now I have the inverse, which then tells me xy must be calculated by taking this inverse, there we have it, written out very carefully, and applying it to 7, 9. So let's see what we get when we do this. So what am I going to start with? I'm going to start with these two here, multiplied by these two. So that's negative 7 minus 27, which comes to negative 34. And that's quite pleasing because I know negative 34 will divide by negative 17 easily. And what else do I have? I then have this multiplication here, these pairs, minus 5 times 7 is negative 35, and then I have to add on the 18, which gets me to negative 17. Again, pleasingly, this will simplify very nicely. So this then gives me 2, 1 for x, y. So I can see that the solution is x equals 2, y equals 1, and there's one unique solution. Now let's return our attention to the graph. Look at that point of intersection. Can you see it's the point with coordinates 2, 1? So in a matrix equation, which relates back to a pair of linear simultaneous equations, if the matrix is non-singular, then the solution is represented, you can see it up here, by the intersection of two straight lines, and of course they intersect at a single unique point. So the whole point of this is to understand the link between the simultaneous equations, the matrix equation, and the graphical representation of the simultaneous equations. So I want you to have a look at the straight lines in the diagram here. The simultaneous equations are as above, so equation 1, x plus y equals negative 4, and then equation 2, x plus y equals negative 1. Now let's set up the matrix equation as we did previously. So look at the coefficients here. That tells me it's 1, 1, 1, 1 being applied to x, y to produce an image of minus 4, minus 1. Now, we can write this as mxy equals minus 4, minus 1, where m is equal to 1, 1, 1, 1. Now, let's explore, as we did previously, what the value of det m is equal to, and you can see straight away it's 0. So that tells us that m is singular. And what does that tell us? m minus 1 does not exist. There is no inverse to this matrix. Now, come back to this. That means we could not solve this matrix equation using the inverse matrix of m. And let's think about why that is looking at the graphical equations, the graphical representation of the equations. It's a pair of parallel lines, and we could have seen that really by looking at this pair of equations up here. Parallel lines will never intersect. That means this pair of simultaneous equations has no solution at all. And this links back to the matrix that is singular. There's no determinant, there's no inverse matrix, and a special case of this relates back to the pair of simultaneous equations being represented by parallel straight lines, so there is no point of intersection. So this second case is a very specific example of what can happen when the determinant of the matrix is equal to 0. You can have no solutions. Now, the third case, you can't see the first line because the two are actually superimposed. But if we could, it would be a red line, essentially, lying on top of this gold line here. So the red line is 2x minus 4y equals 6. The gold line, which you can see, is x minus 2y equals 3, and that's equation 2. Now, what can you say straight away? Looking at those, they're the same equation. One is simply the double of the other. So equation 1 is equal to 2 times equation 2, but essentially they are the same thing. So I could simplify that down by dividing by 2, which would give me x minus 2y equals 3, which is equation 2. They're the same equation. And as a result, graphically, you end up with the same straight line twice. And we say that the lines are coincident. So a nice way of thinking about that might be they lie on top of one another. Or they are the same line. Now, let's investigate the matrix equation here. So, remember, we're looking for a matrix equation mxy, in this case equals 6, 3. So my matrix M is 2 minus 4, 1 minus 2, being applied to xy. So M is equal to this matrix. Now the determinant of M, and I think you know what's going to happen here, is going to equal 0. So again, M is singular, which means M minus 1 does not exist. But we have a different scenario to case 2, because every single point on this straight line, x minus 2y equals 3, is a solution. So we have infinitely many solutions in this case here. So every single point on the coincident straight lines is a solution. Now, that's different to case 2. So when the determinant of a matrix is equal to 0, there are two possible cases for the simultaneous equations. Either you have a pair of parallel lines and no solutions at all, or you have a single straight line and infinitely many solutions, because every point on that straight line will satisfy the equation 2x minus 4y equals 6, because essentially you're only dealing with one equation. In case 1 and case 2, you've got two separate different equations to deal with, so they either intersect or they're parallel. But in case 3, both equations are in fact the same, so of course if you're dealing with one equation and two unknowns, there are infinitely many possibilities for that equation. So we're going to summarise everything we've discussed so far on this last slide. A pair of simultaneous equations can be represented by a matrix equation. Here it is. Now, there are two possibilities. 1, the determinant is non-zero, and 2, the determinant is 0. Let's look at the first possibility on the left-hand side. If the determinant is non-zero, then of course, you have a non-singular matrix M in this matrix equation over here. That means that your lines intersect at a unique point, the equations have a unique solution, and the point of intersection is the solution. So you can see the example from earlier. There's your unique solution at the point of intersection. Now that's a very simple case scenario, and of course the solution can be found by using xy equals n inverse multiplied by pq. So that's a very simple case scenario. When the matrix is non-singular, everything is very, very easy. Now, if the determinant is 0, we've got two possible case scenarios. So either the lines do not intersect, they are parallel, which means the equations have no solution. You can see that over here with the parallel lines. Or the other possibility, the lines are coincident, they are the same line, the equations have infinitely many solutions, and every point on the line is a solution, and you can see that here. So if the determinant is 0, this is where we're dealing with a singular matrix. And this is more complex. So either you have the situation where there are no solutions because you have parallel lines and two different linear simultaneous equations, or you have the solution where there are infinitely many solutions because both your linear simultaneous equations are the same equation. And it's really important that you know and understand the difference between these three cases and why they arise. Just to finish off, I'm going to revisit the third case that we looked at briefly, because we know that there are infinitely many solutions, and there is sometimes a format in which we might give the solutions using a parameter which I might call lambda or t or some other value. So if I call my parameter lambda, what I might do is say let x equal lambda, and then we use this equation here, which is the only equation, and we can then express y in terms of lambda. It's lambda minus 3 over 2, and so we would say that the solution is, or the solutions are, of the format lambda minus 3 over 2. And of course, lambda can take any value here, and that's why there's an infinity of solutions. So you might sometimes be asked to express your infinity of solutions in this third case using a parameter lambda or t or some other letter.